What is up, happy people? This is Jay Saw once again, and today we are going to look at geometric sequences and series. So I want to jump right in and do what we got to do. Once again, if you need to pause this video in order to write down notes or to, um, if you need to restart it and look at it again, you can please feel free to do that. But we can go ahead and check this out. The essential question: how can we find the terms and sums of finite and infinite geometric sequences? And this comes from standard 2.07, where we use recursively defined functions to model and to solve problems. So let's jump right in and talk about what a geometric sequence is, what geometric series are. We're going to look at the differences between finite and infinite geometric sequences and series and what have you. All right. A geometric sequence is a sequence where the terms change by common ratio. So instead of an arithmetic sequence where we add or subtract the same amount each time, in a geometric sequence we can recognize it by looking at repeated multiplication, or each term is being derived from the previous term by way of multiplication, whether it is a large number or whether it's a fractional value. So basically, if the numbers can be multiplied or divided within consecutive terms, then we say that we have a geometric sequence, and the common ratio is often called R. Example, consider the sequence 2, 6, 8, 54, 162. So if we look at this here, what we should notice is that the particular values differ by looking at, let's see if I can make it work this time. If I can't make it work now, I just have to talk it through. I'm gonna be a little sad, but I'm gonna try it. So let's see if we got it, if it's going right. Still not right. Okay, but hopefully we noticed that to get from one term to the next, we're simply multiplying by 3 each time. So we can say something like the current term is equal to the previous term times 3. All right, and then continuing on from there, if we were actually to write a recursive formula, then we would say that we have, okay, a sub n. To get a particular term, we look at our previous term, and we times it by 3, we multiply by 3, and we keep going, keep doing it, and whatever. All right, and we also have our initial state where we have a sub 1 equals 2 as well. All right, the explicit form of a recursive formula is similar to, I wish I could get the screen to right, but it's because I need to show you all this here. Uh, so I was unable to get the screen to type like I wanted to, but one thing I want us to get from here is that our explicit form, we simply look at a sub 1, and instead of adding d as we did with an arithmetic, we're going to continue to multiply by r. So just as we know multiplication represents repeated addition, we know that using exponents that represents repeated multiplication. So we end up with an expression that's an exponential function. Again, this is our formula: a sub n equals a1 times r raised to the n minus 1. That is our explicit formula for a to find a term in a geometric sequence. All right. For example, we have a sub n equals 2 times 3 raised to the n minus 1. This will be the explicit form for the example that we had before. We start with 2, and then we will continue to multiply um, by 3, and we multiply n minus 1 times in order to get the desired result that we needed for this particular problem. All right, so if we had to find the 8th term, again, we would simply plug in 8 for n, and we would get a sub 8 would equal 2 times 3 raised to the 8 minus 1, which is 2 times 2187, which equals to 4374. Pretty straightforward, pretty simple for what it is that we need to do. So hopefully there was no problem there. All right, now I want to go past just looking at individual terms and talk about series. Actually find the sum of these particular sequences. So let's look at a finite series. And the formula that we have for that is simply going to be S sub n. And one thing I want us to keep in mind when we look at these two formulas, which will be provided on the formula sheet. Do I have the formula sheet queued up? No, I don't. So let's look up NC pre-calc formula sheet. All right. And one thing I want us to notice is that on this particular formula sheet, we have a couple formulas, and I want us to differentiate S sub n versus S without a sub n. That's one of the biggest differences. So I want us to see S sub n refers to a finite series, where we're looking at a fixed number of terms. All right, if we have, like, find the first 8 terms, find the first 10 terms, or what have you, we're going to use the S sub n formula in order to obtain that answer. I'm gonna try this again, see if it's gonna write on here. It's still not writing. I don't know why it's doing that, but it's kind of upsetting me. All right, and then so let's look at that real quick, and I'm gonna go back and talk about what S stands for in a second. All right, where are we? Geometric sequences. I got 2 windows open. Here we go. So to find the sum of a finite series, we use this formula. All right. So for example, the first 5 terms of our previous example, we know that a sub 1 is 2. We know that the rate in this case, what we're multiplying by, is 3. So we have 2 raised to the 1 minus 2, multiplied by 1 minus 3 to the 5th in this case. And we're using 5 for n because we're finding the first 5 terms. So n represents the number of terms that we're looking at. So we will plug in both of these instances, divide by 1 minus the rate, which is 3 in this case, and we get 242. And if you wanted to actually go back and look at those first 4 terms and add those together, you should see that they do indeed add up to 242. In contrast, an infinite series just has a simple formula, a1 divided by 1 minus r. And I want to look at that real quick. Let's go back here to a finite series. This particular formula for an infinite series only works if our rate, or the absolute value of our rate, is less than 1. So if we have a number that's less than 1, 1/2, negative 1/2, 0.1, something that has an absolute value of magnitude less than 1, and we raise that small number to a big power, then basically this thing kind of goes away to 0. So in essence, we're just left with a1 times 1 minus 0, or just a1 times 1, or just a1. And you see that's indeed how the formula changes. So an infinite series is a series with an infinite number of terms, and if our rate is less than 1, we say this series converges, which means that the series will actually approach a fixed value. So the weird thing about this is, even though we're adding an infinite number of terms, or an infinite number of numbers, if you will, because the numbers that we're adding become so small and so small and so small, we're in essence adding nothing else to it, and then the entire series itself will approach a particular value, which is found by just simply looking at a1 divided by 1 minus r. All right, just a little trivia. I didn't put it on the slide. I apologize. If this does not hold true, then what we say about the series is that it diverges. So if a series approaches infinity, if a series approaches infinity, then we say that the series diverges. And we really don't have a formula to deal with things like that. But in this case, we do have a formula to look at that, and we'll say that again, the series will converge. So we would go with that. All right. The formula for that series again is S equals a1 divided by 1 minus r. S equals a1 divided by 1 minus r. And what I want to look at is the formula sheet once again. If we go to the formula sheet, you notice S sub n represents our finite series, and S without the sub n represents our infinite series. All right, and the formula for S only works if the absolute value of our rate is less than 1. So that's something we need to make sure we keep in mind. All right, and we have an example real quick. Suppose that our first term is 4 and the rate is negative 0.5. Let's find the sum of the infinite series. We're going to plug in 4 for a1, plug in negative 0.5 for here. So we end up with 4 divided by, basically in essence, 1.5. 4 divided by 3 over 2. That gives us 8 over 3. And that's it. All right. If you have questions or comments concerning the homework assignment, we can do that. Something that we need to watch out for is that if we have an infinite series, even in sigma notation, I want to cue up the assignment that the worksheet that we have for today. I thought I had it queued up. So let's try this again. Let's escape. Right here, right here. Let's look right here. Boom. Um, Even for these ones that have sigma notation, what we want to look at is let's see, for the finite we can plug those in like we did before. We would just write a sequence. Excuse me, we'll write a sigma formula that'll do that for us. For example, number 15. That's the wrong tab. This is what I'm looking for right here. We can do a summation for that as well. So we can go ahead math, and then we're gonna sit there and we're gonna say, let's say x from 1 to 8. Delete x is from 1 to 8, and then we're going to say -2 times 6 raised to the x minus 1. Boom, and let's sit there and do it right there for us. So we're good to go. All right. Now here's the problem. When we have ones like going from 1 to infinity, we cannot put in an infinity into the calculator. But hopefully if we see those infinities, we'll understand that, hey, this only works if that rate is less than 1. So what we have to identify in each of these cases is, hey, for example, number 25, what is my first term? Let's plug in 1. We get 1/3 raised to the 1 minus 1, 1/3 raised to the 0 power. My a sub 1 will be just the number 1. All right. And so we have 1 divided by 1 minus r. And this number inside of parentheses in this case will represent our rate. Here's our rate. And then we can identify the rates for each of those other ones as well. All right. Remembering that this formula only works if the rate, the absolute value of that rate is less than 1. So if we have something where the rate itself is bigger than 1, the absolute value is bigger than 1, then we already know that the sum of that series will be infinity. All right. So with that being said, hopefully we won't have too many questions with the homework assignment. If so, collaborate with your partners, and then all right, y'all do what y'all do. Have a good day, and I'm going. All right, I'll talk to y'all again tomorrow. Take care. Bye bye.